Welcome to everyone. My name is Ömer Mehçu. Today we will solve 5 questions of the homework 1 for probability course. In the first question, a gambling game based on coin tosses is considered. Tossing of a coin continues until either a second head is observed or the coin is tossed 4 times. Let's start with part A. It says that write down the sample space. Sample space can be written in this way. The coin is tossed until a second head is come, or the number of coin tosses reach 4 times. And let's start with part B. In part B, it asks that define and write down 3 events. The answer may be changed from a person to another person. However, we define the 3 events in this way. The first event is coin is tossed only twice. The second is coin is tossed exactly 3 times. The third event is coin is tossed exactly 4 times. And we defined the events like that. In part C, it asks that assign probabilities to your events where the probability law should satisfy the axioms. In this question, we assume the coin as a fair coin and we assign probabilities to each event. Probability of head is 1/2 and probability of tail is 1/2 again. And according to this assumption, probability of double H is 1/4, and probability of these 2 events is 1/8, and the probability of the other events become 1/16. And according to these values, we can say that the sum of the probabilities of these events is equal to 1. And with respect to this result, we can say that the axioms of probability law can be satisfied. In the last part of this question, it is asked that whether this identity is satisfied or not for your model. If true for any probabilistic model, prove the identity. If false, then give a counterexample to disprove the identity. Let's look at the solutions of part D. There is a long solution, however, we will overview this solution. If you look at the first part of the solution, this identity given in part D is satisfied for the 3 events defined in part B of this question. However, there may be some other events for which the identity does not satisfy. And if we define the 3 identity like that, and if you follow this process, you will see that the identity given in part D is not satisfied for the 3 events. Therefore, we cannot say that the identity is generally true for any probabilistic model. In the second question, it says that a cell phone tower has a circle coverage of area of radius 5 km. We observe the source locations of calls received by the tower. This question is a conceptual question, and let's start with part A. Suggest a sample space to model all possible source locations of calls that the tower can be received. Let's look at the solutions. When you look at the solutions, radial distance of the source location of a call from the cell phone tower. That is the sample space. Since the question is a conceptual question, the answers are very short. In the second one, it says that based on your answer in part A, Is your model discrete or continuous? Of course, the model is continuous. It is a very simple part. So we will continue with the last part of the question 2. In part C, using your sample space, what is the event that the source location of a call is between 1 to 3 km from the tower? In this part, we define the event like that. Radius is an element of real number set, and the length of radius is between 1 to 1 and 3. So the event can be defined like that. After this conceptual question, we will continue with the third question. Let's move on with the third question. In this question, suppose you are a contestant, and in the game which you are a contestant, you are offered 8 envelopes of which 7 contain nothing and only 1 contains a grand prize. You pick an envelope, and the host, who knows which envelope the grand prize is in, opens another envelope, different from the one you picked, which contains nothing. At this point, you can switch to a different envelope or stick with your initial choice. Let's start with part A. What is the probability that you win the grand prize if you open your initial envelope? What is the probability of winning if you switch to another envelope? Let's start with these two probability questions. Let's start with part A of the third question. In this question, in part A, it asks that if you select a box, what is the probability of winning the grand prize? Since the grand prize is in only one box, the probability of winning the grand prize in the first choice is 1 over 8. That is a simple part. The second part of section A, part A, it asks that if you select a box, then the host takes an empty box, and then if you change your box with the remaining boxes, what is the probability of winning the grand prize? This is like a Montiel problem, and we should consider the problem like that. In the first step, you will choose an empty box, and the probability of choosing an empty box is 7 over 8. For example, this box. After that, the host takes an empty box. For example, this box. And you choose the remaining boxes instead of the first choice. And when you look at the remaining boxes, the number of the remaining boxes is 6. So the probability of winning the grand prize by choosing the remaining boxes is 1 over 6. So multiplying these two probability, you will find that the probability is equal to 7 over 48, which is greater than the probability of winning the grand prize in the first choice. Therefore, changing your selection is a better strategy. Let's continue with the second part, B. Host reveals a second envelope containing nothing before you make your choice. According to this, answer the questions in part A. It means that the host reveals a second envelope in addition to the first envelope containing nothing before you make your choice. Let's start with the solution of this question. In part B of the third question, it asks that the host chooses a second box in addition to the first box before the contestant changing his first choice. The only change we'll make is to take this box. And now, when you look at the boxes, the only probability change is this one, 1 over 5. because there are only 5 boxes left. And after this change, the total probability of the event becomes 7/40, which is again greater than 1/8. Therefore, this strategy is also better, the first strategy. That is the conclusion. Let's continue with the fourth question. The question is related to our probability course. And in this question, it says that based on data from previous years, it is gathered that 90% of students who do the homework pass the probability course, while 20% of the students who don't do the homework pass the course. It is known that 70% of the students do homework. Let's start with part A. What percent of students pass the probability course? Let's look at the solution. Define two elements. Element A, students who do their homeworks. Element B, students who pass the probability course. It is given in the problem that probability of A is 7/10. And given probability of A 7/10, the probability of A complement is 3/10. That is the simple part. Now you will use the conditional probability given in the question. Recalling total probability law, probability of B can be written by this way, and the values of the probabilities are given in question. By using the values, probability of B can be found as 69%. That is, 69% of students pass probability of the probability course. That is an important conclusion. Let's continue with part B. Of students who passed the exam, what percent did homework? Based on this example, what should you do in the rest of your life? Let's continue with the solutions. In this part, basically, we are required to find probability of A given B. Recall the bias rule. Probability of A given B is equal to probability of B given A multiplied with probability of A over probability of B. Using everything we know so far, probability of A given B can be found as 63/69. Let's move on to the last question. Consider the gambling game in question 1. Define A as the event that tossing game stops at the second coin toss. This time, instead of finding probability of A theoretically, we will perform a numerical analysis, Monte Carlo analysis. If you want, you can see the reference one, and estimate probability of A using MATLAB software. In part A, it says that run the MATLAB code provided below and write down the estimated value of probability of A. That is the simple part. The only thing you should do is you will take the MATLAB code, run, and see the final result. Since there is a randomness in MATLAB code, the results you find may differ slightly. And the answer we found in this question is 0.164 as probability of A. The question can be finished like that. In part B, it says that reduce the number of tries to 100 and run the MATLAB code at least 8 times. Then set the number of trials to 100,000 and again run the code to get at least 8 estimated values. Write the 16 values you obtained. In which case does your estimated value of probability of A vary widely? Comment on your results. Let's look at the estimated values when number of trials is set to 100. The results we find in our MATLAB code is like that. The results may change from a person to another. However, the thing you should see is the variance is very large. One of the results become 0.060 and the other become more than 3 times. If you set the number of trials as 100,000, the results should be like that. Our results can be seen in this way, and if you compare these 8 results with the first 8 results, you will see that the variance of these results is much less than the first one. That is the most important conclusion. And in the later chapters, you will see that the central limit theorem and law of large numbers should dictate that if you increase the number of trials, then the variance will be smaller. That's the result. Let's continue with the last part of the last question. It says that define another event P where trials stop at the third coin toss. Modify the code accordingly and estimate probability of P over 100 trials. The only thing you should change is this part. You will change the outcomes from 2 to 3. Then you will run the code. Let's look at the solutions of part C. The necessary modification, as we said before, is to change 18th line of the code. After making this change, we can estimate probability of P over 100,000 trials. And the result you should get must be very close to 0.192. The variance should be very little because you work with 100,000 trials. As you remember, when you increase the number of trials, the variance should be very low. Today we try to explain the solutions of homework 1. I hope the recitation will be good for you. Thank you for your listening and have a nice work.